about the technology, the importance of it, but more importantly, is it safe? Is it something that we should have as part of our energy portfolio, all the different types of energy that we use here in the United States and across the world. So my purpose is to answer any questions today you might have about the technology. I do believe that nuclear is part of our future, although right now it seems to be heading in the other direction as other forms of energy are taking over the more popular choices here in the United States. So thank you very much for having me, and I hope to be able to answer any questions you might have.
Howdy. I'm Dennis Menard. Believe it or not, I graduated from Chicopee Comp High School in 1965, which I realize is so long ago, none of you will remember it. Went in the Navy after that, got admitted to the Naval Nuclear Power Program. I became a reactor operator on a Polaris submarine. Spent 3 years on a Polaris submarine, so by the time I was 24, I had spent over a year of my life physically underwater. After that, went to UMass, got my degree in electrical engineering, went to work at Combustion Engineering, which later on became ABB, which now became Westinghouse. Spent the first 5 years designing X-core nuclear instrumentation. X-core nuclear instrumentation is literally out of the core, X-core. It's how you monitor power level by looking at neutron leakage from the core. In 1979, I was sent to 3 Mile Island right after the accident as a member of the Industry Advisory Group. Did some neat and very fun stuff down there. Decided to get into the training department just because I got tired of designing one thing. And it was a great thing. I ended up at the San Onofre Nuclear Generating Station as a trainer. About the same time, the NRC said if you're going to train senior reactor operators, you better be a senior reactor operator. So I got myself enrolled in my own licensing class, and I got my senior reactor operator's license from the NRC in 1983. Came back to Windsor, did a lot of training, did design work, did anything that they would allow me to do. In 1990, I got involved with rewriting the federal law governing the operation of nuclear plants. That's the technical specifications, 10 CFR 50.36. See what the heck else. That was done by 1993, did some traveling, Ukraine and whatnot. Started to redesign instrumentation for the Korean units, Newport protection calculators, and ended up back redesigning nuclear instrumentation systems, exactly where I started, and retired last year. And why am I here? I'm here because I was here last year and the year before and enjoyed the heck out of it, quite honestly. What do I find interesting about nuclear power? I lived in it for my whole life, and there's an awful lot out there. But one of the things I would say is about misconceptions, relative orders of magnitude. If you get 1 millirem of exposure, is that going to kill you? No. Well, I certainly hope not. It might shorten your life by 1.2 minutes, statistically speaking. But how much do you get from a nuclear plant? How much do you get from a chest X-ray? If you were at Fukushima, how much would you have gotten? Give you a subtle hint, it's less than that chest X-ray. But that's all I've got to say.
Good morning. My name is Steve Dunn. I'm a professor of geology at Mount Holyoke College. I went to college in Northern California. My first experience with nuclear energy was as a protester at a nuclear power plant that happened to be built in a very bad location at Humboldt Bay. And one of my professors had mapped a geological fault very close to the reactor. And so a lot of us students decided that's not okay to have a potential earthquake right next to a nuclear reactor. So we started spending our weekends picketing this plant. And it did end up becoming one of the first power plants, nuclear power plants, to be decommissioned in the U.S., in large part because it was in an unsafe location. But I had left before that happened. I just had a tiny role to play in that. But then as soon as I left with my bachelor's degree, I started working in uranium exploration. So I sold out and became an exploration geologist looking for uranium deposits. So I did that for a couple years, and then I went to graduate school where I studied geochemistry and formation of ore deposits, not specifically uranium, but all different types of ore deposits. Now I've been at Mount Holyoke for 27 years, and I teach environmental geology and a full range of geology courses from entry to advanced. Not focusing on this topic, but I followed it and I included it in my environmental geology course. So I have this geological perspective on the nuclear industry. And in particular, one of my concerns or things I find interesting is the long-term storage of high-level nuclear waste, which continues to be a pressing issue with nuclear energy. I consider myself an environmentalist, but I also am a realist. I don't think we can do without nuclear energy anytime soon, either globally or in this country. We are a very energy-hungry population, and we need all energy sources at the present time. I would like to see us eventually phase some things out and take great care to preserve the atmosphere and not continue to put greenhouse gases into the atmosphere. So nuclear energy, I think, has a role to play, but I think it also has a lot of interesting issues. I'm here because I'm interested in education. That's my, when I'm not studying rocks and minerals and geochemistry, I'm in the field of education, and I love the reputation of your school, and this is the first time I've been here, and it's a real pleasure. So thank you for inviting me.
Hi, I'm Pocky Wieland, and I've been here a couple of times before too, and I'm really happy. Every time I meet students and talk with Keith, I'm more impressed with this school. And one of the things that I'm hoping to do this morning that actually brought me here was to really kind of thicken the conversation or deepen it, that a lot of the panelists are really know a lot about the technology. And that's good information, because we live in what we often refer to as this information age. And I think information is really good. I'm a Facebooker, and I love to go online to just check things out when I have questions about things like Pandora's box. What is that? What are the origins of Pandora's box? And we'll talk a little more about that, I hope, during our time together this morning. But what I'm hoping to do, and what brought me here, was to get beyond the question of technology, information, and to move to a deeper understanding of knowledge and wisdom. I think nuclear power, I think the discovery of the atom, the splitting of the nuclear atom, was opening Pandora's box. As some of the panelists have said, we've got a big question about what to do with all the waste. And even right up at the nuclear power reactor in Vernon, Vermont, that we're not that far from, that many of us live right downriver from, we still don't know what to do with all the waste there that is leaking some radiation, as my colleague says, not enough to kill you, except for maybe taking a minute or two off your life, unless something untoward happens. So I'd like to thicken the conversation to look at questions like, do we really need nuclear power? And what is the relationship between nuclear power plants and nuclear weapons? That without nuclear power plants, it's very hard to create nuclear weapons. And we know that nuclear weapons have been used not only in the exploding of the bombs in Hiroshima and Nagasaki, but in spreading the nuclear pollution and killing in places like Iraq, where the U.S. has used depleted uranium to basically alter the lives of so many people in Baghdad and other places in Iraq. And finally, I just came back from a week with indigenous people in Washington, D.C. They're from out west, where there are 10,000 open uranium mines. So the scientist went out, discovered uranium, and the big capitalists said, I think we've got something here. So there was a uranium gold rush, if you will, a uranium rush in the 50s and 60s. And those mines that were created, lots of uranium was taken out, pieces are still left, there's still uranium that is polluting the air, the water, the land of not only a lot of indigenous people, but places like Mount Rushmore, and the land that is the breadbasket of this country, where grazing cattle who become McDonald's hamburgers or steakhouse steaks eat grass that has been irradiated. So those are some of the concerns I have, and I'm very happy to be here.
Hello, my name is Andrew Larkin. I graduated from college in the middle of the last century of the previous millennium, so I have some years on you. My father was a radiologist, and he was drawn into the promise of the atomic age. He went to Nagasaki on his own, independently, after they dropped the bomb, and wrote one of the first papers that appears in American literature. In it, he clearly outlines the distinction between the thermal entries of the skin of the victims and the cold injuries caused by radiation. It was the last paper he wrote about in the American, it was the last paper he ever wrote. He developed a 1,000-yard stare of those who have been severely traumatized. In much of the story of World War II, my parents, the greatest generation, were also a silent generation because of their internal war wounds from all different types of reasons. That's a little bit of my family background. When I came of age, there was the question of going to war, and I became a conscientious objector, believing that with the dawn of the atomic age, it created an obligation to become civilized. Before, you could have a war and it was contained within a field because you could only throw rocks and weapons. And now the battlefield has spread around the world. And we do hear, yes, the promise of it, and yet I believe with Pakistan and Pandora's box, we've opened up Pandora's box, and mass extinctions in this country have been characterized. For example, one was a layer of iridium from a asteroid. Alvarez did this work. And today, throughout the world, it's being covered with cesium-137, and there's a slowly developing a layer of radiation toxicity. Indeed, the millirem will not kill you, but then again, that same logic says that buying a lottery ticket will not kill you. But you know, occasionally, people win the lottery on a small bet, and occasionally that single thing on an average doesn't do anything for one person, it potentially kills them. There is no safe level of radiation. The nuclear age was born in secrecy and deception. That's been part of its nature since the beginning. Paley wrote a report in the 1950s, and Paley, head of CBS, a white paper report, was asked to look at the energy future, and he then said, nuclear and oil are dogs, and he advocated electricity, solar, and biomass. It's worth reading because those ideas have been around for 50 and 60 years now. So I'm here to say that I think that opening of the nuclear chimney could well be an unmitigated disaster. And the disaster has already occurred. And although we only dropped 2 bombs, and in Japan, we've dropped 50 bombs over the Marshall Islands, over 200 over the 200 bombs. Above ground testing, you can read about the downwinders, the devastation of people dying of cancer in the United States. The facts are that the nuclear weapons industry has killed more people in the United States than has killed people in the United States. It's a major health risk. Is the reason I'm here, and I'm here to say that yes, there's promise, but yes, it's a bit of a disaster, this nuclear industry, and that and I wrote a blog about this for a while, for radiation safety. I got tired after a couple of years, but I'm disturbed because I am told that it's illegal for a physician to make a diagnosis in Japan of radiation-related illnesses. It is a crime to make that diagnosis. And so I'm here to say, you know, do what you can. As you know, we've sort of made a mess of it, and we're hoping that you can make some sense out of all of this. Thank you for listening.
All right, so you have heard opening remarks from our 6 panelists. In a moment, I'm going to turn it over to Alice Inside, and they can call on you to start posing questions. I think in the interest of time, what I'd like to do is, for each question, have about 3 people respond, give or take, and I'll try to keep score so that everybody has about equal airtime. But that's not like a smart move, so they don't all respond to the same question. We get a lot of questions posed. All right, Alice, it's up to you.
So we grateful that these folks have come out today. Who'd like to ask the first question?
Who'd like to ask the first question?
That's a pretty open-ended question. So it's nuclear fission that is the process, taking a large atom, breaking it into smaller atoms, and releasing significant amounts of energy in the form of high-energy photons that can be converted into heat. How does it work? Well, if you have a uranium-235 atom, and you hit it with a neutron traveling the right velocity, it will split that atom and create 2 neutrons in the process. So now you have 2 neutrons and more uranium-235 surrounding it. When those neutrons hit those uranium atoms, they will split. Each of them will send out 2 more neutrons. So you basically have the opportunity for a runaway reaction of an atomic explosion, because each reaction is creating 2 new neutrons that can carry it much further. In a nuclear power plant, you use something called a moderator to control the neutron flux. So you control the reaction. You get a lot of heat, and that heat will drive turbines, boil water to steam. The expansion will turn turbines and create electricity, just the same as a coal-fired power plant would do that, except by burning coal to boil water to steam and turn a turbine. So it's really the same as an electric coal-fired power plant, except the fuel source is different. I'm not sure that I've actually answered all aspects of your question, but I wasn't sure where you were coming from, so that was my first attempt.
And can somebody handle the second part of the question, which is how do nuclear power plants relate to nuclear weapons? All right, I'll set the timer for 3 minutes.
Okay, in a nuclear weapon, what you're trying to do is get a whole stack of uranium-235, preferably more than 90% enriched. You have to realize that standard garbage-grade uranium out of the ground, okay, is about 0.7% uranium-235. And the rest of it, over 99%, is uranium-238, which doesn't fission, okay? So what you have to do is enrich the heck out of it to make it work. Now, in a commercial reactor, you might enrich it 2 or 3%. I'll explain why in a second. Whereas in a bomb, you have over 90% because you're depending on fast fission to take place of the uranium-235. Fast fission means you produce a neutron, good fission, plus about 200 million electron volts of energy. It goes on, causes more fission, which goes on, causes more fission. And if you've ever seen the old Walt Disney thing with the mouse traps, how it expands. In a commercial nuclear plant, you don't depend on fast fission. You have a much, much lower enrichment that could never fast fission. And what you're depending on is the fact that most elements, including uranium, are what we call 1/V absorbers. The tendency of uranium to absorb a neutron is a function of the energy of the neutron. 1/V means 1 over the velocity. Velocity is proportional to the square root of the energy. So what you have to do is slow this damn neutron down. Now, when a neutron is born, its most probable energy is about 0.78 million electron volts. That's pretty fast. That's way too fast. A neutron wandering around in this room has 0.025 electron volts. Okay? It's a lot slower. So you have to slow the neutron down. How do you do that? How many people ever play pool? How many people ever seen anybody play pool? Okay. You get the idea. You take a cue ball, which is the same mass as the ball you're hitting, and you hit it, and what happens? Cue ball stops or slows down, or if you didn't hit it right, it deflects. The ball you hit took off. You have now transferred the energy from the neutron, from the cue ball, to the ball you're hitting. Now, if you look at water, water is made up of what? Made up of water, H2O, 2 parts hydrogen, 1 part oxygen. Hydrogen consists basically of a proton and an electron, which weighs almost nothing. A proton has a mass of 1.007825 atomic mass units. A neutron is 1.008665 atomic mass units. So the mass of that proton that you're hitting is approximately the mass of the neutron that's coming in. What does that mean? You ever try and play pool where you're hitting a bowling ball? Doesn't work. Why not? Because the cue ball bounces right back off. If you want to transfer energy, the object you're hitting has to have approximately the same mass as the neutron coming in. That's why pool works. And that's why we put hydrogen, water, in a core. Because what it does is it slows the neutrons down. After about 18 collisions, you're down to about thermal energies, 0.025 electron volts at room temperature. At that point, uranium has a high tendency to absorb the neutron. That's how commercial fission works. Essentially, you get the neutron produced from fissioning. After about 18 collisions, 1/50,000th of a second, it's slowed down to the point where the next uranium atom absorbs it. Okay? Then it fissions. Okay. Close enough.
One more person,
Sure, I think that's a very interesting discussion. I think, though, that people ought to look at, Leslie Groves spoke about the bombing of Nagasaki and Hiroshima. They built 2 different bombs. They built a uranium bomb and a plutonium bomb. And afterwards, they picked a few cities to leave alone so they could study the scientific effects. And Groves wrote this interesting book in which they sent people into Nagasaki and Hiroshima, and they compared the effects of the plutonium bomb and the uranium bomb. And they concluded the plutonium made a better bomb. And so to make plutonium requires nuclear reactors. Well, there's different ways of making it. But we can't discuss this without looking at Eisenhower's Atoms for Peace, in which there is a lot of resistance to nuclear war technology. And they manufactured a public relations program called Atoms for Peace, and they gave nuclear power to Pakistan, Iran, and Israel.
I wanted to say that Mr. Bernard was talking about the speed of things, and one of the things I was thinking about was, wow, this is going really fast, and like even if I was in college, I'd be I'd be taking just tiny little bits of notes. I wouldn't be trying to capture everything that he was saying. We are filming today, and so I'm going to put this whole thing up on the website so that you can go back and get the exact quotes of what these experts are saying. So for now, what would make sense for your note catcher is if you can just capture little sound bites. For example, I've written down Pandora's box, depleted uranium in Iraq. And I just put that next to the person's name who said it. YouTube uranium-235. Father wrote one of the first articles, right? And so I can go back later, watch the film, and get like the exact quote and information. So I hope that helps.
My question to you guys were, what is some of the downfall from nuclear medicine? Jay.
When you say downfalls, can you be a little more specific? What are you getting at?
So like, I know that sometimes it can be helpful for like cancer and using radiation, x-rays and all that kind of stuff, but also what's harmful about it?
Okay.
Well, I'll just say a couple of things. A few years ago, I broke my arm, and I was very happy to have a little nuclear medicine, a little X-ray that showed just what had happened. And as far as I'm concerned, I think the biggest downfall is the overuse of it, particularly in mammograms. And I think the other downfall, or the other problem, that goes back to that Pandora's box is what in the world do we do with all this nuclear stuff, whether it's from hospitals or from nuclear power reactors. And I just want to say I was really impressed as I was listening to the scientists talk, because I'm not a scientist, but you may have guessed that already. And I can appreciate that the appeal of particularly theoretical physics, and I wonder how we could play with this in the classroom in so many different ways without having to go into the arena of dealing with things like nuclear reactors that we know we don't have the solutions for. And I think it's hubris to think about continuing to create nuclear reactors when we know that there are so many ways with renewable sources. If they were given the same kind of economic incentives, if the tax write-offs went to solar and to wind generation of energy that the nuclear power plants do, that I think we would not have nuclear power plants. What I think of as one of the hallmarks of a failed capitalist system. Adding just another dimension to that.
Just very quickly, this is a health question. My father died of a brain tumor. This used to be one of the occupational exposures of radiologists, and now they've had the techs move in a little closer, and the radiologists are a little safer. Now it's an occupational risk factor for cardiologists because they're sitting right there in the radiation field. So there are complications. There are also reports of the total deaths, follow-up complications. People worry about cancer, but people also get heart disease, and there are estimates of the most dangerous thing these days is actually nuclear medicine for the number of people who have, not immediately, but people get radiated and they have second cancers and stuff like that. It's out there, it's a real problem, and the people are getting sick from it and dying from it. My father did.
Okay, I'm going to do a little bit of something first here, something that hasn't been brought up, but it's basically getting basic units down straight. When we talk about radiation, we're talking REM, we're talking sieverts. The big question is, how much is damaging, how much isn't? I'll picture that's something when we talk about radiation everybody would like to know. Okay, I can throw a number out right now that says A typical mammogram or a typical GI X-ray gives you 40 milligram of radiation, and that's a lot lower than it was several years ago when it was about 300 milligram. What the heck is a milligram? What does that mean? How much peril does that put you in? Anybody want to know? Yeah, okay. I've got 3 minutes to do this, so I'm just 2.5 minutes to do this. So I'm going to kind of go up the scale in terms of the amount of damage done for different amounts of radiation. The radiation, the way I use it is in REM, Roentgen Equivalent Man. The SI units for it are sieverts. A sievert is 100 REM. But forget that, I don't have the time to go into that. What you're going to see almost in any source you want, if you want to look at radiation damage or radiation exposure, exposure limits, anything like that, is if you get less than about 10 rem of radiation, okay, there is no evidence of any damage to anything whatsoever. However, they're going to assume that you linearly will get damage all the way down to 0. That's the assumption that's made to be conservative, which is good. Makes it easy for me to do my job. If you raise your radiation up above 10 rem, that's an acute dose. That's a sudden, very quick dose. You can see very, very slight changes in a few people in the red blood cell count that returns to normal. But the point is it has an effect. When you raise that up to about 50 rem, 25 to 50 rem, it's a bit more pronounced, and you can see it, but nobody realistically gets sick at that point. Now I'm talking acute doses, not doses spread out over your whole life. I'm saying a dose within 24 hours. If you get it up to about 100 rem, okay, that's 100,000 millirem for what it's worth, you end up getting about 10% of the people who will get some form of radiation sickness, which sounds like the flu, their white blood cell count changes, red blood cell count changes, and they get better. If you get up over about 200 rem, 200,000 millirem, okay? Of course, you're going to wonder how much do you get yourself sitting here. We'll get to that later. 200,000 millirem. Now, 40, 50%, the numbers vary depending on what you read, but are going to feel flu-like symptoms, get sick, but they're probably going to recover unless you're really, really compromised in some way. If you get up to 450 rem, not millirem, rem of radiation, that is called the LD 50-30, lethal dose for 50% of the population in 30 days. You don't want to be there. Okay, it wipes out your red blood cells, you're probably going to get infection, you might die of pneumonia or something like that. And then it gets worse as you get above that. Now, that's 3 minutes? Ah. I never answered. Anyway, it's 400...
Keep going.
It's 40 millirem for a typical chest x-ray, 40 thousandths of a rem, which is bug dust type stuff. It's also, well, never mind.
You can Google it. You
We'll find a way.
Okay, so my question is, do you think there's a safe way to dispose of nuclear waste? And if so, what is it? And is it cost effective? Yeah, so do you think there's a safe way to dispose of nuclear waste? And what was the second part of this?
And is it cost effective?
And is it cost effective? What do you mean by is it cost effective?
Like, I know like one of the ways, like they say, is like shooting it off into space, but it costs way too much money to be practical. Is like the way we currently use cost effective, or is the safest way possible?
Okay. I haven't heard from either one of you, so we want to take it first, and we'll see who else wants to come.
All right, I'll give it a shot since I've worked in this industry for so long, and one of the issues that we have in this country is the storage of nuclear waste. Just a tiny bit of history, we used to reprocess fuel back at the very early years of nuclear technology in the United States. That was stopped back in the 1970s. So as we produced waste fuel, it was reprocessed, and then it would be essentially reused, but we don't have that technology in the United States. So since then, at all the commercial nuclear power plants in the country, we've been storing our spent fuel. And now we're at the point where these spent fuel pools are reaching their capacity, in some cases have exceeded their design capacity, and we're storing them on site in what is known as dry cask storage. So we put them into very robust stainless steel canisters. They are then put onto a pad. They've got a massive concrete overpack, and that will be the interim storage for waste in this country until we have a federal repository. The industry's been paying into a fund since the 1980s to fund what we thought was going to be Yucca Mountain out in Nevada. Currently, that's not one of the avenues that is being pursued by our government. So we don't have a place to put nuclear waste with the exception of on-site right now. A number of the different technologies that are being looked at include, burying it underground. Because what we're really trying to do is wait for a point in time, many years into the future, where the fuel is no longer dangerous. But these interim storage facilities are very, very safe. They're designed for many hundreds of years. And I think the solution is to find a national repository for fuel, so it's put in a safe place, it's being monitored properly. As far as the cost, it is very expensive because it's a very specialized technology. It costs us many millions of dollars just to store the fuel at the power plants we have them right now. So the best solution from an economic standpoint is to find one place to put them safely that we can agree is right for the technology.
Okay, so when it comes to nuclear waste, I agree with what you're saying about Yucca Mountain. The biggest concern with Yucca Mountain is politically, no one wants, transporting nuclear waste in their backyard. Unfortunately, rail systems were designed to go through cities, so they go through cities with nuclear waste in these dry casks. So that is a major hurdle that regulators and the nuclear industry are trying to overcome. I sat in on a meeting with two bright new engineers, nuclear engineers, who were proposing a new nuclear design. We're not currently there right now, but the design that they were proposing was for a reactor that could use waste fuel produced from the majority of the nuclear plants in the world and reuse it to about 90–95% of its energy capacity. The remainder fuel after that, the half-life the fuel is not as much of a risk to the public at that point. You have less you have to worry about putting it in storage or burying. So it greatly reduces the environmental impact of that.
So there's a couple pieces to this question. The big picture is there's over 30 countries that use nuclear energy and have high-level radioactive waste. Not a single one has a long-term solution for the waste. And this has been going on for 50 years or more. If it was easy, it would have been done. It's clearly not easy. And I could imagine most of your lifetime going by and having the high-level radioactive waste still sitting on the sites where it was produced in the U.S. If you haven't noticed, Washington, D.C. is a little bit broken these days and not very effective at setting new policies. As Joe indicated, Yucca Mountain in Nevada, a lot of money was invested to create what would be the first long-term high-level radioactive waste storage facility. I think it's a very well-situated location. It's got all the right features geologically. It would be hard for us to find a better place to do it, but politically, we don't seem to have the will. It happens to be right next door to where above-ground nuclear testing took place in the U.S. So there is a vast wasteland right next door that's unsafe for any other use. It's a very dry region. One of the big problems with long-term storage underground is that if the water table were to rise, and then your waste storage facility becomes submerged by water, groundwater, you're likely to run into a problem. Yucca Mountain, it's unlikely that that would happen there. No one can predict geology too far out, but the Environmental Protection Agency, when they set the mission to find a long-term storage place, they said they wanted a location that would be geologically stable for 10,000 years. That was what they required. Geologists cannot agree that there's anywhere that 10,000 years is stable. And that's one of the problems with Yucca Mountain. Again, I'm just one person, but in my opinion, I don't think we're going to find a better location than that. But to give you some perspective, that location is about 1 hour's drive from Death Valley, which is the driest place in North America. And Death Valley was a freshwater lake 18,000 years ago. So in 18,000 years, that area has changed from very wet, a large freshwater lake, to now being the driest place in North America. And we are saying that we want a place that will be stable for 10,000 years. It's pretty hard to say. I do want to add to something Mark said. When you turn uranium fuel into high-level waste by using it as fuel, what you're left with is much more radioactive than the original uranium. It's much more dangerous. And it actually takes 100,000 years for that waste to get down to the same level of radiation as the original uranium. So high-level radioactive waste stays dangerous for a very, very long time. After 100,000 years, then it decreases fairly rapidly. And as two people have pointed out, what is the real problem is we don't reprocess the waste. If we would take the wasted fuel and reprocess it, then we would not only produce new fuel, but we would greatly, greatly reduce the quantity of the high-level waste that needs to be taken care of. I'm sure my time is up. I could talk more about the technology of preparing it for storage and so on. Sweden may become the first country to actually start storing high-level waste in the ground. And I might mention that in-the-ground storage is the only option on the table. We are never going to shoot it into space. We're never going to store it in the oceans. It's going to be in-ground storage. That's the only option.
Can I just add something to that? Because I think the Swedes are putting it in a mountain, actually. And one of the questions is, because it's radioactive for so long, what symbols would you use to let people who come thousands of years from now know that it's dangerous?
Because of half-life, will that alter your opinion on being pro-nuclear power?
Right, so yeah, essentially, how does this issue of half-life affect your opinion on nuclear power? Nice segue question.
I would just briefly say, if the half-life were very, very short, we wouldn't have such a great problem. But because the half-life is so very, very long, we create a real long-term problem.
Well, I think I'm still pro-nuclear, even with the half-life situation, because it's a problem that needs to be solved. It's a fascinating industry, and I truly believe that there is plenty of room for improvement and innovation, and we need to spread the word about the benefits of nuclear, the safety of nuclear, but also inform you of, the situations that we're dealing with half-life, and, the more people that get involved and study the science, the closer we'll get to finding a solution.
The question of half-life, people have a sense that this is a surgical procedure where they bring in a couple of atoms and then they split it and they sort of,
you can see these charts, and Helen Caldicott makes the point that every possible element and every possible isotope variation is created for these nuclear reactors. Not a lot, but some. And you create the entire periodic table, all of them different half-lives, all of them with different characteristics. Very short lives, boom, it's gone, it's not a problem. The intermediate ones seem to be the most active. The ones that go on for, I know, we're supposed to be appalled by the ones that last 100,000 years, but that's a pretty slow decay. I think, biologically, you have to worry about the things that iodine, cesium, but you make everything, any element you want. It's like putting a thing in and putting it in the Waring blender. You get all these different pieces.
Okay. In terms of the production of fission products, when uranium fissions, it fissions generally into two daughter products. They almost never have the exact same weight. So you end up with a light group and a heavy group. The light group centers around strontium, strontium-90, weight of 90, okay? And the heavy group centers around 130, or cesium-135 or cesium-137 or something like that. It's the ones that have an intermediate half-life that are the big problem. Uranium itself, uranium-238, has a 4.5 billion year half-life. I've touched uranium fuel rods. There's basically no radiation, because that means if you have a half-life of 4.5 billion years, it takes 4.5 billion years for half of it to decay. So per unit time, you get very little. On the other hand, you take something with a very short half-life. Let's talk about iodine-131. Iodine-131 is used for thyroid work, to do thyroid sufficiency scans. It's got a half-life on the order of 7 days. Well, that's good, because it's very quick, it's over, after several days, it's gone completely, it's decayed away. But in the meantime, it's very radioactive, okay? The ones that are intermediate, cobalt-60. Cobalt-60 is a half-life of 5 years. That means once you produced it, half of it's gone in 5 years, and another half of that's gone in 5 years, and another half of that's gone in another 5 years. So the ones that last an intermediate amount of time, like cesium-137, about a 40-year or 30-year half-life, they're the ones you worry about. Not the real short ones, they decay away. Not the real long ones, because their specific activity is so low. That's just background.
It doesn't matter. Cesium-137 behaves exactly like potassium. And the ocean is largely made out of sodium and very little potassium. And we as species, starting way back on the evolutionary table, have developed this great desire to soak up potassium wherever we see, so that the cesium-137 will be significantly concentrated, because the body can't tell the difference between potassium and cesium, and it gets in the cells, and that's one of its mechanisms.
That gives me an in. Okay, to talk about potassium, something that's rather interesting is one of the things I've got here. Eating a banana gives you approximately 0.1 microsievert, which is approximately 0.01 milligram of radiation, every banana you eat. Now, why is that? That's because potassium, one of the isotopes, is potassium-40, okay? And it decays radioactively with a half-life of about 1.2 billion years. That's a long time, but that's why you have it. It's not bootstrapped to any other decay chain. If it had had a shorter half-life, it would have all decayed away by now. But here's the point. You eat potassium. You have quite a bit of it. You have a lot of it in your bones. It's used a lot in metabolism. Your body is producing a radiation dose right now of approximately 40 millirem per year. I'm sorry, 39 millirem per year is the official number, due to the potassium in your bones and in your body. That's potassium-40. You can't get rid of it or you die. You are radioactive. As a matter of fact, if you're cuddling up next to somebody sound asleep, you will get approximately 0.05 microsieverts, which is 5 microrem, which is about half of 0.01 millirem of radiation per year from sleeping next to that person, because he's radioactive. Okay? Oh, by the way. And you also have Carbon-14, you probably heard of it. Carbon-14 only gives off 1/10 the energy. It has approximately the same number of decays per second, which is about 4,000. That's right, you're decaying about 4,000 decays per second of potassium, and close to 4,000 due to carbon-14. But the carbon only has about 1/10 the energy level, so the actual radiation dose is lower. But the bad news is a lot of the carbon is in your DNA. You don't want any radioactive dose in your DNA, but guess what? It's in there. You can't get rid of it. It's part of what makes you, you. It's part of the 360 millirem per year you're exposed to, even if you don't take any medical x-rays.
All right, Valentine's Day is time to get another question. All right, so what are the benefits of nuclear power plants?
About 20.
Oh, somebody else. So I was going to talk that much stuff.
Okay, so the benefit of nuclear power plants, there's a couple benefits. First off, nuclear has the highest availability of all the energy sources. It's available 90% of the time, day and night. Solar, is only about 25% available. Obviously you're only producing power when it's sunny out. Wind is about 34% available. In addition to that, based off of fuel, capacity factors for nuclear are at 90%. Right below that is geothermal at 66%. Coal is only provides about 60%, and natural gas is about 47%. The nice thing about nuclear power plants is that you really only refuel them, every 1.5 to 2 years.
I guess I'll add a couple of things. One is from my perspective, it's given me a job for 34 years, so that's obviously a very good benefit. But it's really a developing technology. We have kind of the classic designs that we've been operating now for over 40 years. But we talked about, some of the emerging technologies, and one of the things that I think is very viable for the future is the type of plant that uses the spent fuel from other plants, so becomes more sustainable. And there have been projects that our government have hired, very, very smart engineering firms to look into those, but thus far they haven't gotten off the ground because they're not taken seriously. If you look at our energy picture in this country, all of the sources we have today play a role. Solar and wind were mentioned, but again, they're not very reliable. The wind doesn't blow, the sun's not out, they're not making energy. Nuclear power has been 20% of this country's energy picture for many, many years. Over in Europe, France, for example, much, much more. And part of the problem is, as we continue to use our natural resources, as we continue to dig up coal, as we continue to try to find different ways of getting natural gas, they are going to go away. There's a limited source of that. So we need to have things that are carbon-free, that don't hurt our environment, and they need to be part of our energy future.
In my mind, the greatest advantage of nuclear energy is that it does not produce carbon dioxide. And so 20% of our electricity coming from a non-carbon producing source is enormously helpful. I would say if we were to burn all the fossil fuels on the planet, there is no future for humanity. I think there's no scientist who would argue with me. If we burn all the fossil fuels on the planet, we will make the planet uninhabitable for animals like us. The global warming would be incredible. And we have in the geological record evidence of times that are called hothouse Earth periods, when CO2 levels were many, many times higher than they are today. And there's evidence of mass extinctions that go with that. So I think we have to find a way to leave fossil fuels in the ground. We have to find alternatives. It's going to take a whole generation or more to do that. Nuclear energy can help us get there, but it has its own problems. And so you are really picking your poison. But I think that the one advantage that hadn't been mentioned is the greenhouse gas-free aspect.
Well, I think there are a couple of questions about that. I'm not sure it's so quite greenhouse gas free, but I loved your honesty down there about what is the goodness of nuclear power, and I think I was about to say I think nothing, but you got a job, and a number of you have jobs thanks to nuclear power. So you know you're supporting yourselves and your families and contributing to the gross national product. But I think I want to go back to something because you're talking a lot about how good this is, and we've got this reactor right up the highway from us that isn't being decommissioned. Is that costly? How come it's not being decommissioned if it's been closed down? I heard that, and I said I didn't think there were any, but then I realized that people have jobs, and so that's something good. And I think it's good to think about all these different ways you can be very good scientists. But I think if we don't look at the underpinnings, like the Pandora's box issue, that so you do the science, but what are the results?
A lot of these things are being made by the same companies, GE, Westinghouse. They can do one or they can do the other. With regard to nuclear weapons, Barack Obama has a plan to put $1 trillion to update our nuclear arsenal, $1 trillion. And I believe that $1 trillion could be spent on better projects. And, you know, nuclear technology actually is, Dennis Kucinich had a group that wrote a paper about the carbon footprint of nuclear power. And it turns out, you know, they actually send trucks out to the mines, and they run on carbon. And then there's this whole carbon footprint from the carbon, the distillation, the separation, and then these things are made and they're manufactured and they send around. And some people have actually made the point that much like ethanol, with ethanol actually it takes as much energy to produce it as to make it, so it's sort of a net zero thing. And people suggest there's actually a significant carbon footprint associated with nuclear technology because it's manufactured in a carbon-based technology.
Okay, so for companies like Westinghouse and GE, we do not have any ties to nuclear weapon development. Our number one priority is safety to the public. No, we would never, our research and our designs, that is our priority. As far as the CO2 footprint is concerned, yes, there is a CO2 footprint for nuclear. However, if you compare it to that of coal, gas, solar, and wind, the only one that comes close to matching us is wind. So for statistics here, so coal power plants, they emit 820 grams per kilowatt hour of CO2. We're 70% less than that. For gas, we're 40% less. They produce 490 grams per kilowatt hour. Solar, we're 3 times less. They produce 41 grams per kilowatt hour, just producing panels. And wind is 12 grams per kilowatt hour. That's what a nuclear reactor is at, 12 grams per kilowatt hour.
My question is more directed towards the activist on environmentalist panel. So when you say that you disagree with nuclear power, does that also include nuclear weapons? And if so, how do you suggest our country defend itself against other countries who have this technology and who are currently advancing it?
Well, there's only one country that's used nuclear weapons on civilians, There's only one that's dropped 2 big bombs, and I think we all know which country that is. They're the good guys, right? I have a good friend who talks about this and says, you know, once upon a time, slavery was legal, but it isn't anymore. Once upon a time, women didn't have the vote, and we do now. One day, hopefully in our lifetimes, and certainly hopefully in yours, people will say, once upon a time, people used to go to war. They killed one another for what? But we don't do that anymore. And that's, I think, part of the human trajectory that I want to see. I want to see scientists be as creative as possible and to use all those parts of our brains. But I also want us to look at what is it that humanity is all about and how do we find ourselves in our own place on this planet. I happened to be in Paris during the climate action talks, and there's a lot of debate about that. In fact, there were a couple of people who actually said nuclear power was a good thing, but of course we were in Paris, which parallels the US with its nuclear power plants. But I think what we need to do is to look at what kind of world we want to create and what are the kinds of things that the promise of nuclear power had, carbon-free, always available, electricity, the turn of the switch, and to look at how in this changing world in which we live, in this climate chaos in which we live, do we want to live our lives? And where does nuclear fit in? And I think as far as the nuclear power and nuclear weapons, it doesn't.
Right, so the question was, how do we defend ourselves? I believe, Tatiana, correct me if I'm wrong, how do we defend ourselves against other countries that have nuclear weapons? Is that?
Yeah, because it is a reality that we face. So my question is, although there might be only one country who has, you know, uses technology other than us that hurt us, it is a problem that we face, especially when we have everything. So how does that relate to current problems going on? Yes, we've dropped on Hiroshima and it is questionable, but I feel with Dr. Dunn as well, over this in a sense, I think this affects us in the future, our generation. So my question was, how do we defend ourselves, and how do us basically, I guess, run up to the power because of how we do it? If that was pulled back, how would we continue on? Because now it's
So the best way to defend ourselves against that is education and information. And, you know, people need to know that if they use a nuclear weapon, they're not just hurting the country that they're dropping it on. There are side effects. You know, wind carries radioactivity. So, so that's a big thing. If they are educated about that, they might be thinking. As far as, yeah, I lost my thought there.
So when I was a kid, we had drills in school. We had drills that were nuclear attack drills, and we would all jump under our desks at command. A totally futile exercise, but they had us do that on a monthly basis. This was in the 60s when there was heightened alerts that nuclear war could break out at any time with the Soviet Union. The politicians came up with a term they called mutually assured destruction. And it could be argued, and many political scientists make this argument, that the development of nuclear weapons resulted in one of the longest periods of world peace ever because of mutually assured destruction. That if you use the bomb, we will retaliate, and life on Earth will be basically destroyed if It's mutually assured. I find it interesting that the acronym is MAD. But we have rogue nations today that are threatening. We have Iran developing nuclear capabilities, and we have a new treaty in place that's supposed to stop that. One thing I would say that's a little relevant, I'm not answering every aspect of your question, but it's very unlikely that a country could develop a nuclear weapon without our knowledge. It requires the transport of certain kinds of equipment and the building of certain kinds of facilities, and we have satellites everywhere, and our State Department would certainly know of a uranium enrichment facility. You couldn't really do it secretly. So we know what everybody else is doing, and yes, education is certainly a key. If we could spend more money to educate women globally, we would have far fewer problems. It's been shown time and time again. If you want to put your money in helping nations, put it into the education of the women in that country, and you reduce poverty rates, you reduce birth rates, you raise everything. So I happen to teach at women's college, so I have to admit that.
As I'm passing this over to Andy, I'll just say the biggest underlying piece is to teach and to understand making justice.
Yeah, I think that I would suggest people reading Smedley Butler, one of the most forgotten war heroes of the 20th century. He wrote a book called War is a Racket. We have these vast oceans. You know, we're pretty well defended. Our founding fathers warred against wars and foreign entanglement. We have troops, special operating troops, acting in 60 or 80 countries around the world. For some reason, we've taken on the job of being the world's bully. And we're part of that bullying is being a nuclear bully. And at some point, I think the future of civilization depends upon the United States having a fundamental transformation and giving up the role of being a nuclear bully and being an advocate for peace. Oak Ridge, Tennessee.
Okay, remember what I mentioned, that most of the uranium out of the ground is uranium-238, with less than 1% being uranium-235. And essentially that's neither good for bombs nor is it good for nuclear reactors. You need uranium-235, so what they do is they enrich it by basically converting the uranium. One of the methods is to convert the uranium, the raw uranium, if you will, the ore, into a gas. Now, it's pretty tough to convert uranium to a gas. I mean, it's got a mass of 238. It's one of the densest elements there is. But you can, uranium hexafluoride gas, and then they pass it through nickel filters, little tiny pores. And since chemically uranium-238 is identical to uranium-235, they're not going to chemically separate it. But what they can do is you put it under pressure, and it turns out the uranium-235, at least gas, is going to go through preferentially rather than the U-238. And you have to do this again and again and again and again. It's a very long, involved process. And essentially what you end up doing is enhancing the ratio of 235 to 238. If you can get up 2 or 3%, put it in a reactor. It takes a lot more thought than that. You have to get the right amount of water to moderate and all that. You can build yourself a reactor. If you get up over 50%, they call that bomb-grade uranium, but I believe most bombs have well over 90% uranium-235. It takes a lot of work to do that. The other way, and this was not available during the Manhattan Project back during World War II, is centrifuges. Again, what you're doing is you're preferentially spinning it, and you're making the U-238, which is heavier, go to the outside, and the U-235 to go to the inside again and again and again. So anybody can get uranium. I mean, it's not like the stuff is that rare. It's just that trying to make it in a useful form requires getting rid of the U-238 and enhancing the 235 in some ratio.
Tremendous energy input to this.
It takes a lot of energy, but nowhere near what you get out of it. I mean, you're spinning a centrifuge. That's it. Did that answer your question, by the way? Yeah, good.
I agree with everything Dennis said. That's exactly right. What I would add, just for those of you in chemistry, is that fluorine gas is the most electronegative element known. When you use 6 fluorines to 1 uranium, you actually make it a uranium fluoride gas, and that's what's used. Fluorine is incredibly toxic and dangerous. One small puff and you're dead. So only experts can handle that. Uranium, we talked about the radioactivity and the danger of that, but uranium is a heavy metal. All heavy metals are dangerous and terribly toxic to humans. So if you handle the uranium wrong, you're also sick or dead. So you're dealing with really nasty materials here. You don't want to try this at home, but we've just told you how. Fluorinate the uranium, make it into a gas, get aluminum tubes with screening and use it in centrifuges. Aluminum is useful because it gets a thin coating of fluoride and then it stops reacting, and so you have to use that material. And again, you cannot do this anywhere on the planet that Big Brother isn't going to know that you're doing it. Again, we are sort of the world's policeman in that way. So it can't really be done in secret. And it's very time-consuming, very dangerous. You have to have very sophisticated laboratories in order to pull it off. But it is being done, and it's being done in a number of countries. We're not the only ones.
You know, there is great promise. There was a thought of great promise, but we haven't mentioned 3 Mile Island, Chernobyl, Mayak, which is a Russian city that blew up in the 1950s, or Fukushima with these nuclear reactors. And yes, these have a great promise, but when you have a bad day in a nuclear reactor, it's a really, really bad day. And that bad day that occurred on 3/11 5 years ago continues to react and continues to put toxic stuff into the Pacific Ocean. And like the events at Fukushima are not over, and yet we're continuing to run more and more of these. They're all at sea level. All these things are being stored on floodplains. How much evidence do we need to say, stop? And people believe that Fukushima is a Japanese issue, but actually this is part of the GE Corporation that's exported to Japan. They're very loyal, their footprint. And we've been remarkably fortunate that the GE Mark I boiling reactor that four blew up. We have 40 of these on the coast in the United States. At what point do we say, enough?
Drops mic.
So at this time, I would invite each of our panelists to give a summary statement, just 1 minute. And the question is, do costs outweigh benefits with nuclear technology, or is it the other way around? And, which one do you want to start?
I think the cost.
Cost and benefit, it's not worth it.
Ditto, but I'll use my other 50 seconds to say that I really encourage you to think about the kind of world you want to live in and to look at all these things, whether it's what these corporations are doing, what we're going to do if we continue to create more and more nuclear waste that we do not have the answer to, and keep in mind Pandora's box, and put that in perspective so that our hubris, because the science stuff is so exciting, isn't it? But where does it go?
So what I want to use my minute to say is that, that science is, that the barriers between different divisions of science have all broken down. Science is sort of one big body of knowledge that all bleeds together, and it's wonderful. The theory of the atom has changed human history, for the most part, for the better, no question about it. But there are difficulties, there's problems. What we need are well-informed scientists who are broadly educated, that have a moral center, that can be leaders. And we need politicians who will listen and who will be educated. And I'm looking out at you thinking, many among you are going to be filling these roles. So, you know, I wish you a lot of luck. You know, you'll need it. You'll need to work hard. If you go into science, don't forget your humanity. And if you go into the humanities, don't ignore the science. It's all, you know, we are all in this together. As far as the cost-benefit ratio, I think that in the long term, we need to get away from nuclear. We need to get away from fossil fuels as well. We need a sustainable planet is what we need in the long run.
I'm not going to add anything to that. Right now, it certainly is cost competitive. I know solar is trying to get down to the point where it is roughly cost competitive with nuclear and other forms, but it's dropping all the time, so I'm not going to say anything about that. I'd like to have solar panels on my roof. But I'm going to take the rest of my 45 seconds or whatever to ask you to assume that I'm a charlatan, that I've been lying to you all along. And what I would do is I would go on the internet, and there are so many different sources of this information that it's ridiculous for me to come up with one. But this is a rather nice chart some of you may have seen that talks about different relative levels of radiation from different relative sources. This is where the mammogram is 40 milligram, used to be 300 milligram. That's an old version of this. If you were sitting on the site fence at a commercial nuclear power plant, you got the maximum permissible radiation dose permitted by law. It would be 25 milligram, less than a mammogram. If you were at Fukushima at the town hall for 2 weeks, it's 10 milligram. That's worst case. So, again, how much do you have to do before you see any changes? You've got to get about 10 rem before you see anything at all, okay? In terms of cancer, which is a whole different issue, we're not talking about acute doses. Again, every milligram cuts off about 1.2 minutes of life. And if you don't want to believe this, which is synthesized from a lot of other stuff, go to the NRC website on radiation dose calculation. You can calculate your exact dose based on your elevation above sea level. Down here you have about 23 milligram per year. If you go up to where I am, right, 23 milligram per year. If you go where I live, which is over 1,000 feet, it's closer to 23 plus 28 milligram, okay? You go to Colorado, you're sitting there at about, if I'm not mistaken, about 60 milligram, okay? So don't go to Colorado if you're worried about radiation. Plus the 90 milligram that you get from background from the soil. Down here, we don't get that much. But that's another story. Please, don't believe me. Get something like this. Again, the radiation dose chart, or there's an NRC website where you can calculate it. Go with it. Most of what I've said is here, including...
Thanks again for the opportunity to spend a little time with you. Obviously, I've been in this industry for a long time, and it's been a very challenging and a very rewarding career. You're the future. You will decide whether or not this technology goes forward. But the reason this technology has challenges regarding its cost is because we're not working collaboratively to come up with the right solutions. The majority of the cost of building these plants today are to get them permitted and put into places that they're being built, because we're not working together. There are divides always on whether or not it's the right thing to do, not in my backyard. So I look to you to lead the future, look to you to make a decision whether this is part of our future. And I can tell you it needs to be part of it. And I think there's a lot of really smart people who will figure it out. Good luck.
So I do believe that the benefits outweigh the costs. If you really look at the energy profile that we have, it's okay. Energy profile, there's a lot of options for producing energy. But really, if you did away with nuclear, no other alternative energy source is really there right now to take its place. Germany is trying to eliminate all nuclear power plants in their country, and as a result, they're going to end up their plan is to go wind and solar, but they're going to end up having to buy electricity from Russia, and Russia's using nuclear, so is that really anti-nuclear there? But the other thing with nuclear, you're increasing the number of jobs. Fuel price for nuclear is very stable. It's uranium is available worldwide. And as far as costs are concerned with radiation, you're exposed to radiation on a daily basis. You all have cell phones, I'm sure. You all turn on the radio in your car. There's radiation all around us. Get it from the sun. So, I truly believe that the benefits of nuclear outweigh the cost.
You wouldn't come away from this with an answer, but I hope you came away from this with a lot more ideas about what you need to research, what kind of questions you can ask when you're doing your research. I'd like to just thank all of our panelists. If you want to take a moment just to come up and say hello to our panelists, I'm sure they'd love to get away from the bright lights and say hello.
Go.